Okay, so in this part, I'd like to just say a few more basic things about lim sup and lim inf. There's going to be, I'll justify why they actually exist, and then there'll be one theorem about what happens for a sequence that converges. Okay, so let's just sort of recall from last time. We defined the lim sup, and we basically said that the lim sup Sn is defined as the limit of a certain sequence. And I'm actually going to call it Vn. That's what the book calls it. And this notation is going to be useful. So just bear that in mind. So this is where Vn equals the supremum of Sn for n greater than capital N, right? And lim inf Sn is the limit of un with a similar thing with infimum. Okay, so just as a fact, Vn is decreasing and un, is increasing monotonically. So that's the basic reason why we can say that the limit of Vn makes sense necessarily, right? Because we showed before that for any monotonic sequence, the limit has to exist. Either it's plus or minus infinity or it's some finite number, okay? So just, to justify this a little bit, why is Vn decreasing? It's because, so consider the step from Vn to Vn plus 1, right? This basically amounts to, right, in Vn, we're taking the supremum of a set of the Sn's. And then in Vn plus 1, we're taking a supremum of basically the same set, but we've discarded one element, right? So we discard Sn plus 1, which is the first element in the set that we're taking the supremum of. So we just throw it out. The supremum can only get smaller, right? Because either Sn was large to begin with, in which case when we throw it out, then, like if it was the biggest element, right, then after we throw it out, the sup can get smaller. If it was small to begin with, then when we throw it out, nothing happens because there were other things in the set already that were bigger than the element that we threw out, right? So by discarding this thing, we can only make the supremum go down, okay? And then there's a sort of a flipped logic for the infimum. So that's why the lim sup and lim inf have to exist for every, so the conclusion here is lim sup and lim inf always exist. They might be plus or minus infinity, but they do always have some value, okay? So let's move on to our theorem here. So this is basically theorem 10.7 in the book, which is about lim sup and lim inf for convergent sequences. So it's stated in two parts, but it's effectively, actually let me write them up here. It's effectively an if and only if statement. They just have to separate the two directions because one of them you have to word slightly differently. So this direction is if the limit of Sn exists, then the lim sup Sn equals the lim inf Sn, and that equals the limit of Sn as well. Okay. So all three of them agree they have the same value. And this one is if the lim sup Sn equals lim inf Sn, then limit of Sn exists and has the same value as the other two, right? So yeah, let's prove this. So in the first part here, first of all, there are kind of two cases to consider, right? Because by saying lim Sn exists, all we're saying is that it doesn't diverge chaotically. It either diverges to plus or minus infinity, or it converges to a finite number, right? So the plus or minus infinity cases we have to handle slightly differently. So let's deal with that first. So case one, the limit, or yeah, let's say Sn goes to, let's just consider positive infinity for now. And let's just show that that the lim sup is also positive infinity, okay? And in fact, let's just phrase it this way. We want to show that the limit of vk is also positive infinity, where vk is the sequence from before, right? It's the sequence of suprema. So how do we do this? Well, we let m be a real number, and we're going to show that vk get bigger than m, right? So the thing about this is that like the relationship between Sn and vk or vn or whatever is actually very straightforward, because I mean these are just like, you know, these are just sort of measuring, you know, specific values in the sequence Sn, but they're not, there's no complicated functions being applied here. So actually it turns out that the capital N we can get for the sequence Sn ends up also working for vk, right? So so there exists a capital N such that for all n greater than capital N, Sn is greater than m, right? That's just because Sn diverges to infinity. So then, but this means vk is greater than m for all k greater than n, because vk is the sup of Sn for n greater than k, and these Sn's have n greater than n as well, right? If k is bigger than capital N and little n is bigger than k, then little n is bigger than capital N, so Sn is bigger than m, right? So there are things in this set that are bigger than m, right? Necessarily. So that tells us that vk is bigger than m. And so that's it. So vk goes to infinity as we wanted, right? Okay, so that's the infinite case, and the lim inf is dealt with similarly here. So and for minus infinity, everything's also basically the same. So now let's move on to the finite case. Well, yeah. So let's say Sn converges to some, whoops, not m. It's ridiculous. All right, Sn converges to some real number, S, right? Okay, so in this case, what we'll do is actually a little bit tricky, or not tricky, but it's sort of clever, but this is actually going to debut a new kind of a technique or sort of a trick that will become useful many times more in the future. So you should definitely pay very close attention to what's going on here. Well, the first thing is, the first bit of this is like not, I'll point it out when I talk about the specific trick. Okay, but the overall strategy is like not that complicated. So what we're going to try to do is show lim sup Sn is less than or equal to S less than or equal to lim inf Sn. Okay, if we can do this, then we're done, right? Because we already know that the lim inf is less than or equal to the lim sup. So that means that the inequalities go in both directions, which means that all three of them have to be equal to each other, right? So, so that's the sort of overall strategy, okay? For this, to show lim sup Sn is less than or equal to S, what we're actually going to do is show that lim sup Sn is less than or equal to, or I mean, it doesn't matter, but is less than S. Actually, do they do it? Oh yeah, less than or equal to S plus epsilon for all epsilon greater than 0. Okay, so this here is what I was talking about. This is the kind of the trick here that will become useful again later, and it's something that I think, in my experience, it seems like something that a lot of people feel uncomfortable with when they first see it. Okay, just think about this for a second. If you can show that some number is less than or equal to another number plus an arbitrarily small number, right? Then it's not possible that this number on the left here could be bigger than this number itself, right? Because if lim sup Sn in this inequality were actually bigger than S, then you would be able to find an epsilon that was small enough that S plus epsilon was actually smaller than lim sup Sn, right? So the fact that this is true for all epsilon, so let me actually, highlight this, really draw attention to this for all, okay? For all epsilon greater than 0. The fact that it's true for all epsilon greater than 0 is what guarantees that lim sup Sn will actually be less than or equal to S itself, okay? So that's the tactic, all right? So I'm gonna erase this now. So here's how we do that. So, oh, whoops. Let epsilon be greater than 0, right? Then there exists a capital N such that Sn minus S is less than epsilon for all n bigger than capital N, right? So this means, in particular, Sn is less than S plus epsilon for all n bigger than capital N. So what this means is S plus epsilon is an upper bound on the set of Sn, right? So I'll just write that. Upper bound on Sn for n bigger than n. So V capital N is less than or equal to S plus epsilon, right? Because V capital N is the sup, it's the supremum of this set, so it's the least upper bound. So it better be smaller than S plus epsilon, right? And then since Vn is, or V, let's say Vk is decreasing, this means that, well, Vk is less than or equal to S plus epsilon for all k bigger than n. But then this means, as you might remember from a homework problem, or at least from maybe the squeeze lemma or whatever you could use to argue these things. But when you know that a bound like this holds for all the terms in a sequence beyond a certain point, that means that the same bound holds for the limit, right? So the limit of Vk is less than or equal to S plus epsilon, right? But then, so that's the same as saying that the lim sup Sn is less than or equal to S plus epsilon. This is true. This argument, we made this argument for an arbitrary epsilon, right? Well, here, I'll just write this. So epsilon is arbitrary. That shows us that the lim sup Sn is less than or equal to S, like we wanted, okay? And then for the other argument, it's just the same thing, but flipped around again. So I'm gonna skip that one. The book skips it too. Maybe it would be a healthy exercise for you to try to complete it yourself, but it looks almost exactly the same. Okay, so that completes the first half of this theorem. And luckily the second half is actually a lot easier, so. But this less than or equal to S plus epsilon trick is, like I said, it's very useful. Okay, well, actually, okay. So for 2, the book skips these cases too, and I'm gonna do it too. Let's just only consider the case where lim sup and lim inf are both finite instead of the infinite cases. So oops, lim inf Sn equals S, some real number, and we want to show that Sn converges to S, okay? So let epsilon be greater than 0. Then remember, so like I was saying before, the relationship between the sequence Sn and the sequence of, you know, Vn's and or Un's or whatever is actually very straightforward. So what we can do is we can just say, you know, then there exists a capital N such that Vk minus S is less than epsilon for all k bigger than capital N, and uk minus S is less than epsilon for all k bigger than capital N, right? Well, actually, okay, let me be careful about this. So this is for N1, and then here we're gonna say N2. There exists an N2 such that this is true for N2, but then take capital N to be the maximum of N1 and N2, right? This common trick coming back again. So we just want to make sure that both of these two things are true at the same time. Then let little n be bigger than capital N. Well, actually, I don't even need to do that, right? All I have to say here is, you know, v capital N is, yeah, let's just say this. So v capital N is less than s plus epsilon. This means Sn is less than s plus epsilon for all n bigger than capital N, right? Because v capital N is the supremum of all of these Sn values, right? And then, so similarly, Un is greater than s minus epsilon. This means Sn is bigger than s minus epsilon for all n greater than capital N. So Sn minus s absolute value is less than epsilon for all n bigger than capital N. And we're done. Okay? So yeah, because it's just because even a single term in the sequence of VKs, right, is enough to bound all of these SNs above by S plus epsilon, and a single term in the sequence of UKs was enough to bound these all below by S minus epsilon. And once we have both of those bounds, those combine into this absolute value bound, which is what we wanted, right? So that's all for this video. And then in the next one, I will introduce Cauchy sequences, which are a very important concept.